Welcome back to Practical PyTorch. Last time you fit a line by hand with nothing but tensors. Now you meet nn.Module, the container that holds layers. You will build the same kind of model the easy way. The from-scratch fit built a model out of raw tensors, a weight, a bias, and a forward pass. PyTorch ships all of that as a layer you can drop in. The single weight W times X plus B you wrote by hand generalizes to nn.Linear. It is the same idea, scaled up to many inputs at once. This video meets the container that holds layers, nn.Module. Then we stack two layers with a nonlinearity between them. This video has 4 parts. First, from W times X plus B to nn.Linear. One layer, its weight and bias. Second, stacking layers. We use nn.Sequential with a ReLU between them. Third, the activations. ReLU, sigmoid, and softmax. And fourth, why the nonlinearity earns its place. 2 linears are really 1 linear. First, from a single weight to nn.Linear. One layer holding its own weight and bias. Recall the from-scratch model. Pred equals W times X plus B with one weight by hand. And here is nn.Linear, 784 in, 128 out. It makes its own weight and bias for you. This is not new math. Instead of one weight, nn.Linear holds a whole weight matrix. The single times becomes a matrix multiply. X times W transpose plus B, both the weight and bias have requires grad true, so the loop learns them. Take that one layer, nn.Linear, 784 in, 128 out. Ask it for its parameters. The weight has shape 128 by 784. The bias has one number per output, 128 in all. The weight reads out then in. That is the transpose people expect at first, so say it plainly. One bias for each of the 128 outputs. Now the second part. We stack layers and drop a nonlinearity between them. Add a second layer, nn.Linear, 128 in, 10 out. It takes the first layer's outputs down to 10 numbers. The 2 layers join here. The out of the first must match the in of the second, 128. But watch out. So far every step is still just multiply and add. 2 linear steps in a row are still linear. Drop a ReLU into the gap between the 2 linears. Now the flow reads linear, ReLU linear. ReLU zeros every negative number and passes the rest through. It has no weights, nothing to learn. But placed between 2 linears, it lets the pair learn what one layer never could. nn.Sequential chains the layers in order. Hand it the layers top to bottom. First, the linear from 784 to 128. Then the ReLU. Then the linear from 128 down to 10. nn.Sequential is itself an nn.Module. Call model of X, and it runs each layer in turn. This is the exact pipeline the figure just drew. Push a batch of 64 through and watch the shape at every arrow. Going in, X is 64 by 784. After the first linear, 64 by 128. After the ReLU, still 64 by 128. It changes the numbers, not the shape. After the second linear, 64 by 10. The batch of 64 rode along untouched. Only the 2 linears change the last number in the shape. The ReLU leaves it alone. For anything past a straight chain, subclass nn.Module. In init, you name the layers. The first layer, FC1, maps 784 to 128. The second layer, FC2, maps 128 to 10. Then forward says how the input flows. It runs FC1, a ReLU, then FC2. Init names the layers. Forward says how the input flows through them. This builds the same architecture as the sequential above. Only the random starting weights differ. The class form leaves room to branch. Loop over model.named parameters. It hands you every learnable tensor. Print each name, its shape, and its size. There are the 4 tensors, 2 weights and 2 biases. You hand this whole list to the optimizer, exactly like W and B before. The names 0 and 2 are the layer positions in the sequential. The ReLU at index 1 has nothing to list because it has no weights. All 4 tensors hold 101,770 numbers. Now the third part, the activations, the fixed rules you place between layers. An activation is a fixed, weight-free function. ReLU zeros negatives and keeps the rest, the default between hidden layers. Sigmoid squashes any number into the range 0 to 1, a single probability. Softmax turns a whole vector into probabilities that sum to 1. Now the warning from the lost lesson. Softmax gives probabilities for reading a prediction, but when training with cross-entropy past the raw scores, the logits, cross-entropy softmaxes for you inside the loss. A softmax at the output would apply it twice. Run all 3 on the same 5 inputs. ReLU flattens the 2 negatives to 0. Sigmoid lands every value between 0 and 1. Softmax gives 5 numbers that add up to 1. That sum is the tell. It is a probability distribution over the 5 slots, which is why it ends a classifier at prediction time. The last part, why the nonlinearity earns its place. 2 linears, it turns out, are 1 linear. Take the 2 linears and delete the ReLU between them. The gap is struck out. Nothing bends the line now. Compare the pair to a single nn.Linear, 784 to 10. Same shape in, same shape out. The stacked pair and the single layer print the same numbers. They match to 6 decimals. The tiny gap, about 6/10 millionths, is just floating point dust. With no activation, stacking them adds no new power. A linear is a straight map. Chain 2 straight maps and you get 1 straight map. A single nn.Linear could do the same job. The ReLU bends the line between them. That bend is what lets a deeper network learn shapes 1 layer cannot. Let's bring it together. nn.Linear is the handwritten W times x plus, b its weight is out by n, and it makes the bias for you. nn.Sequential chains layers. Subclassing nn.Module with init and forward does the same, with room to branch. ReLU, sigmoid, and softmax are weight-free rules. Model.parameters hands every weight and bias to the optimizer. And 2 linears with nothing between them collapse to 1. The nonlinearity is what makes depth worth stacking. One more check before we go. 2 nn.Linear layers with nothing between them. What single layer is that? Pause and predict. It is a single nn.Linear, 784 to 10. 2 straight maps compose to 1 straight map. The trap is thinking 2 layers must beat 1. With no activation between, they are exactly 1 layer. You have the model now. nn.Module its layers and the activation between them. Next, datasets, data loaders, and batching. These are the two classes that feed a model its data in batches, and that is where the batch dimension B on the shape tags comes from. See you there.